All right, so similar to all the other stuff we've been doing with these module 3, it's helpful to look at the terms first, right? And this one says it's a quarter horsepower. That's some sort of power. Do we know if it's power in or power out? Well, let's look at our equation sheet for motors. Okay. I saw the word DC motor, so I come to DC motor and I look inside this box right here. Right, everything inside of this. And it tells me right here horsepower is on the output side. And that's also just practically speaking, if I have a motor, I want to know if I got to turn a screw with a motor, if I got to lift an elevator with a motor, I want to know how much usable power it has. So that horsepower is its output power. Okay, so this one is P out. 28 volts, there's our V DC, and efficiency is eta, which is always P out over P in every engineering class and every thing, even in life. If you refer to efficiency, you may not think of yourself as a system, but if you think about how efficient you're being, you know, if I'm carrying bricks from my front yard to my backyard to make a patio, like how efficient am I being is a matter of how much power am I using to move these bricks. And someone else comes over and they're more efficient because they use a wheelbarrow, whereas I'm carrying it with my hands. They're carrying more bricks at a time. They're more efficient than me. You know, you use that term efficiency. So how many bricks am I pushing out compared to how much energy am I using? That guy with a wheelbarrow, he's more efficient. Okay, so what current can we expect to draw? We're being asked to find I in part A. In part B, it says if the machine constant is kV, well, it gives us another constant there. Determine the torque out, the output torque. So in this case, we're finding T out. It says right here, if we ignore mechanical losses. So I'll say P mech loss, because that's what the equation sheet calls it, is 0 watts. We ignore them. Look on the equation sheet right here where it says mechanical loss, right? It's saying that this is 0. It's saying that as far as this arrow goes, you know, like the arrow of the system in this formula is like that. There's nothing going out to mechanical loss. So everything that is being developed from electrical is going to my output power. There's no friction along the way. That makes sense. That's what if it would also mean the same thing if it said if we ignore friction or if it was a frictionless system. If it wasn't a frictionless system, I would have to take into account that formula. But in this problem, it says I can ignore friction. I can ignore mechanical losses. And it says calculate the rated speed in RPM. So we're being asked to find RPM. That is not omega, right? Omega is in radians per second. RPM is revolutions per minute. So let me make sure we start right. Yeah, so it says what current can we expect to draw? In current, and I'll just write it down, but is going to be this P in VI. And note on this, these are DC motors, so we're back to where it's just VI. There's no complex power, there's no apparent power, there's no reactive power. It's just P equals VI. I have V, I need I. How can I get P in? Well, I have a P out and I have efficiency. So if P out is equal to 1/4 horsepower, right, and it says 746 watts to 1 HP, that's on your equation sheet. On the output side, right here, 1 horsepower equals 746 watts. So my P out is 186.5 watts. If I say efficiency is P out over P in, well, if I need P in, then I need P out divided by efficiency. 186.5 divided by 0.96, and I get 194.27 watts. That's my P in. So now if I'm going to solve for I, Pn divided by V, Pn 194.27 watts over the V is 28 volts and I is equal to 6.94 amps. One thing to note about power out and power in, your output power will always be less than your input power. So that's a sanity check for yourself. If you calculate an output power that's greater, you've now created energy. That's not how conservation of energy works, right? And you can even tell the width of this line right here is smaller than the width of that line right there, right? Or the length from the here to here is, those are different. P out is always less than P in. So if you did your math backwards and you accidentally multiply by the efficiency, to get your P in, that's a sanity check for you. 194 is greater than 186.5. Good to go. Okay, so there's part A. Part B, it says, if the machine constant, kV, determine the torque out. So think about this. The power developed, I said, is equal to the power out, since the power of the mechanical loss is 0. So if the power of the mechanical loss is 0, the power developed is that. And if I have power developed as an equation, let's go back to the equation just so that you're not taking my word for it. Okay. So the power, we're trying to get to this torque, right? That's the torque out is going to equal, right there, that torque load. The P out, torque load, that's the same as saying torque out. I have the power out, so what I need is omega. And how can I get omega? Well, I have my machine constant, and I now know that my power developed is equal to that. So I can solve for omega. Okay, so if I say PD is equal to KV I omega, omega is equal to PD over KVI. PD is 186.5. The KV is 0.2139. And my I is 6.94. My omega is 125.6 radians per second. So now if I needed the torque of the load, which is the T out, right? Power developed divided by omega. Power developed is 186.5. Because I could also say the power out. Maybe that's more clear because I'm saying the torque out. So the power out is 186.5 and the omega 125.6. And my torque out comes out to 1.485 Newton meters.
Sir?
Yep.
Why didn't we just use the torque developed equals kV times IA formula?
We could. The reason I didn't is because in this case, the mechanical loss was 0. But if the mechanical loss wasn't 0, then the torque developed and the torque out wouldn't equal each other. So I'm showing you those steps that you're right, we can skip those if you wanted to say the torque out is the torque developed because there's no mechanical loss. But if there was a mechanical loss, you would need to be sure to include that as you solve for it. The 400 level problem might even have that. I'm not sure. That's a good question because mathematically, yeah, they are going to be the same thing because mechanical loss is 0. Last one is calculate the rated speed in RPM. This one's pretty easy. The formula on the motor up here in the top says how I can get RPM using omega. Omega equals 2 pi RPM 60. We'll write that over here in orange. Omega equals 2 pi RPM over 60, but I need RPM. So I put omega times 60 divided by 2 pi, and I have 125.6 times 60 divided by 2 pi, and RPM is 119 or 1199.4. In the real world, no one ever puts RPM in anything except whole numbers. So if you wrote, 199, that would also be fine. You could even round it up to 1200 RPM, because think about on your car, that's how it shows it, as the revolutions per minute. You can see the motor spinning. It's always in large whole numbers. So if someone said 1200, that would also be acceptable.